Today's episode is about traces and the Kleene star. So let's start with the basics. We have an alphabet. An alphabet is a finite non-empty set of symbols, as you can see here. So we write it with a sigma. So this is a sigma, and here we have a set, and we have the following elements in our set. Next up is its size. So here you just count the number of elements you have in your set and get the size. Simple, very simple until now. One thing to know is that each of these symbols represents an activity, as you can see here. So a string is a finite sequence of symbols, and that's representing a trace. A trace, you can see other videos to see what is a trace and how many traces make a log, of course. Here now, you can count the elements you have in your trace, and it's very simple. So you have 3 here, you have 3 here, and an empty trace would be 0. So with your strings, you can make multiple operations. So for example, here you have A, B, and C, and you can stick them together with this sign and make one string together. So that's very simple. Now with the identity, here the empty string, it doesn't matter if you put it before or after, it doesn't matter to you. It's always going to result in the primary string you had already. And one thing to know is that order matters. So AB is very different from BA. So that's something to always remember. So let's talk about the Kleene star. So the Kleene star is all finite strings over our alphabet, sigma, and this includes the empty set. So let's say our alphabet is as follows. So this is our alphabet, A, B, C. One thing you need to know is that the empty set is here, but we don't write it. Now, sigma to the 0 will give you just the empty string. So just this. Now sigma to the 1 is A, B, C. So that's very simple. So it's just these are the elements of our alphabet. And now, iteration by iteration, what you're gonna do, so between sigma to the 1 to go to sigma to the 2, you have your alphabet, A, B, C, and you're gonna do a concatenation product, meaning that you have the elements here, and you're gonna every time concatenate 1, 2, 3 times, and that's gonna create the elements here. And then from B, 1, 2, 3. The same thing from C, 1, 2, 3. So you have 3 elements here. Our alphabet is 3. Now you're gonna find 9, because from every element you're gonna create 3 elements. And the same idea goes from here to here. So from every element, so for every element here, you have your alphabet, A, B, C, and you're gonna concatenate. And that's gonna give you this. So one thing to notice is that every individual string is finite. So here every string is finite. But if you're gonna keep on to the infinite, you're gonna find infinite elements, of course. And our Kleene star here is the join operation between all of these sets. So this to the infinite, of course. And here sigma plus is the Kleene star without the empty set. So without this one. So one thing to understand in process intelligence is that here you have ABC, but each of these letters represents an event. And together the string represents a sequence, of course, and it represents our trace. So that's one thing, and it's part of our Kleene star, because Kleene star is all the possibilities, all the finite possibilities that you can create from your alphabet. So here I wanted to mention one thing, just to recap the previous ideas that we have spoken about. This is a finite set, and it is included in our Kleene star sigma. On the other hand, this set is infinite. But here, our Kleene star in itself is infinite, but the elements in it are finite. So that's one point. The other point is that, so this is a zero string, this is the empty language, and this represents one string. So these are not the same. This and this are not the same. Because this, if you see the number of elements here, is actually 1. The cardinality, if you count the cardinality of this, it's actually 1, which is not the case of this one. So to give you a perspective, we have our sigma star, which is the bigger set. So it's the infinite set that represents all the finite sequences that you can create from your alphabet. Inside of that, you have your model language, which in itself can be infinite. The thing is that it can be infinite, for example, if you think of a loop. You can keep on repeating the same loop, and that's an infinite trace. And inside of that, you have your reality. You can never have an infinite loop in reality. Your traces are finite by definition. And the general idea is that you are trying to find a model that's a good generalization of your reality. That's why we need our sigma star and the Kleene star, because we need to define discovery formally. Because in a way, you need to think of a log as a multiset. So here we introduce the notion of prefix and suffix. We have the example of W. So let's say we have W, and W, you can split it in UV. You can take this part, call it prefix, and this part will be suffix. For example, A, B, C. A is prefix, BC will be suffix. One thing, so this is the set. So this is the set of all the prefixes of ABC. And as you can see, ABC is a prefix to itself. The reason is you can take ABC, stick the empty string here, and say, okay, ABC is the prefix, and the empty string will be the suffix. And the same goes for the suffix, but from the opposite side, of course. One important thing is also the substring. So B here is substring of ABC. So other definition you need to keep in your mind is sublanguage. So here L1 is sublanguage of L2, which actually means subset if you think about it. So for example here L1 is subset of L2 or sublanguage, as you can see AB. And one thing to understand generally is that you have your log, you have your model. The conforming traces are the sublanguages of both. So let's recap the full video. First of all, we have our alphabet, we have our sigma. So it's a finite set of activities. Then we have strings. Strings over sigma are the traces. And epsilon here is the empty trace, and the bars are to count the length of your trace. So this to count the trace of your length. Then we have concatenation, which is used to glue traces together, and you have epsilon. We use epsilon to represent identity, meaning that, yeah, in layman terms, it adds or removes nothing, basically. Then you have the Kleene star. So the star here is the operator, and it's the Kleene star. This, we call this sigma star. So it's all finite traces. So it's the infinite set. It's an infinite set of all finite traces. Then one trace is, of course, an element of sigma star because the trace is finite, and this is the infinite set of all finite traces. A language is any subset of sigma star. So for example, our model, the language that represents our model, we saw this earlier on. Then a log is a finite sublanguage. Finite even though sigma star is infinite. That's one more thing. The log is, of course, represents reality, is also finite. We have spoken about prefixes and suffixes. And then one last point was discovery. And in discovery, we are approximating a finite log language by a model language. So this point we have spoken about earlier on too. Everything related to discovery, conformance, these are all operations on these sets. So that was the video for today. If you like the content, please like and subscribe and follow me on LinkedIn.